Hi, everybody.
Hello.
Here we are again, lecture 7. We'll wait a few minutes for other people to join in too, but if somebody has questions about the assignment or about anything else, um, feel free to ask them now, and we'll see if we can address them uh, right now. Here's a question. The assignment instruction mentioned getting a linearized array by using data. Is it necessary to do this? Is it necessary that we do this, or is it okay to completely eliminate the use of linearized arrays in the code? Okay, so yes, you can completely linearize, get rid of the linearized arrays, and that is the end goal. Um, uh, the point that there is a dot data can be useful intermediate. Like you might not have gotten rid of linear arrays in some of your functions, and to pass, so you could do function by function. That's the point. Let's wait one more minute and then we'll start. Okay, I think we can get going. Um, Marcelo, if you haven't started the recording yet, could you?
We are recording already.
Excellent. Okay. All right. So today we are going to look at libraries, and not the kinds that have a bunch of books in them, but software libraries and how they fit into the scientific computing landscape. And the reason for this is that code is bad, which seems like a strange thing to say in a course on scientific computing, but it all boils down to a big difference in how scientists view code and software developers might view it. For a scientist, code is an asset. It produces something, it does a computation, it gives you a result. So code is an asset because it makes things possible. On a software, from a software developing point of view, code, however, is a liability. Every line of code you write is something that needs to be maintained, something that could have a bug, something that somebody could complain about. And so software developers don't like to write a lot of code. Well, those that are paid by line of code do, but they don't like it. They have to. But code in software development is a liability. Um, so if it's not an issue now, it could become an issue in the future. And as we already sort of saw, the maintainability of code is important. So if there is an issue, having less lines of code means that it's easier to find the issue. Now, what makes this a little bit worse in scientific computing is that scientists aren't writing code because they like writing code. By far, they like to write code because they want a solution to a problem. And so they don't really care if it's a quick and dirty solution as long as it gets results. And if this was the only time that this computation or this code was used, then one could sort of motivate or understand that. But that is almost never the case. This code will be passed on or used again. And so that causes headaches later in the development process. So these quick and dirty solutions that can sometimes be very clever and do give you an answer lead to code that you later have to fix to be not so quick and not so dirty. And that's called technical debt. So whenever because what you're doing is you're getting a solution before you've properly invested the time to do it well, and so later you'll have to reinvest the time. You have to pay back that the time that you skipped. And the longer that takes, the longer you wait with that, the harder it will be to understand those solutions. So that's one way to get around that is to write better code. But an even better way around that is to not write code at all. And you can do that because there's a lot of code that has already been written. A lot of scientific algorithms, scientific computing algorithms have been written. They can be reused. So you don't have to write them. You don't have to reinvent the wheel. You just have to find that piece of code that already does what you need to do. And so the solution to having liabilities in terms of code is to code less, to reuse and recycle code that's already out there. And that's what libraries are for. So libraries are collections of typically functions or frameworks or what have you that solve at least a subsection of your problem already. And so there's different libraries for different functions, for different applications. But by using those and by using that people have already spent the time writing those libraries, you will not have to write any code for that part of your computation. And so you will not have this liability. You can sort of pass on the burden of having to maintain that on the developers of that library. And if it's a well-established library, that gives you more confidence. Like a lot of these libraries have been worked on longer than just say a 4-year PhD. And people have made their careers writing or maintaining that library, and so they tend to be of pretty good quality. Well, the established ones anyway. Now, libraries can be seen as modules. We saw modules already, but they are. So what we're going to go into here is the sort of the nuts and bolts of how to use libraries, and it will be somewhat Linux specific, but not really in its principles. But what it comes down to is that libraries are modules that can be reused in other projects, right? And so let's start with a modular code, and let's see how we would turn that one of the modules of that modular code into a library, and then we will better understand how we're using libraries and why we have to do the things that we do with these libraries. So suppose we have a fictitious application called thisapp.cpp, and it has a module called helper that has a .c. This is supposed to be .cpp file, a .cpp file, and a helper header. So it has the header file, the interface, and the implementation, .c. And so its makefile is going to look something like this. There is a rule to make this app, which is just linking two object files together. So this app is over here, and those two object files are compiled with the compiler, the flags, the -c to just compile it, the -o, much as we've seen before, and we've put the compiler name G++ in a makefile variable cxx and the flags in cxx flags. So this is a very simple makefile to have two files basically. We have the main file that is in this app, and we have a helper, which is a module. Okay. By the way, feel free to ask questions as we go along, even if you still have sort of questions about makefiles. It's important that these are clear rather than that we race through the material. Okay, so now we want to reuse this app. So suppose that this module, sorry, the helper module. So suppose we were writing another application, and we want to reuse helper. And suppose that helper is a very well modularized module, so that it doesn't have global variables, and all that we should have to do is in that other application include the header file and link it with the helper.o. So how do we do that? And the idea is that we shouldn't have to recompile helper.o because it's a module, it's standalone. It doesn't change if I put it in another project. It's not all that changes is that that other project uses the functions that are already in helper. Okay, so we want a way to reuse this helper module, well, only sort of using the helper.h, which is the implementation that I have to include in a new application, and the helper.o that I have to link to. So the first thing to do is to put it somewhere where we can sort of always get to it. So the modules so far have all lived in the same directory as the rest of the code, which is not so unusual, but that means that it would be strange to have another project that has to know where yet another project lives to resolve all of the file dependencies. So we're going to move it to some directory. And just for the sake of brevity, I've called that location HLP. That's, you would never do this because it's a relative path, but let's just say that there's some directory HLP, and then under that, I'm going to create two other directories. And that is sort of a standard convention, at least in the Unix or Linux world. Underneath that, what we would call the root directory of this helper module, there'll be an include directory that will contain all of the header files, in this case only one, and there'll be a lib directory, and that will contain all of the object code. And so in this case, it's just helper.o. So moving these files, helper.h and helper.o, over to those directories, that then, it doesn't really matter, but then this old app could be pointing at this directory, and then the new app also. Now, one thing that makes that a little bit trickier is that now that we've moved these files out of the current directory, the compiler can't find them unless we tell them where they are. And so there are some standard directories that the compiler will look at for header files and object files. That's the current directory, and for the ones in that we include with angular brackets, those are also some standard directories that it searches in. But these are not part of those. We chose where to put this. The compiler can't possibly know that it should look for helper.h and helper.o. So we have to rewrite the makefile a little bit so that the compiler knows that. And what we really have to do is we have to tell the compiler where this stuff lives. So the CXX flags, in other words, the flags to the compiler, have to change and have to have this dash capital I extra option, extra argument, that then is followed by the directory name where things live. So by doing this, the CXX flags, this compiler will look in the directory HLP/include. You can put a space in between the capital I and HLP or not. It's optional. It doesn't really matter one way or another. Yes. So now the compilation will work again. It will still search the current directory as well. I actually forgot if it prepends or appends. In other words, if there's a header, a helper.h, both here and in the current directory, I am not entirely sure who would win. But in any case, this yes, you could have both. And so other header files that are still there will still be found. This adds to the directories. It doesn't just make it that directory. So the compilation works, but the object file has also moved. And so the only way I could do that in this first step is to just bluntly put in the absolute path to this object file when I'm linking it. So the linking stage doesn't have as nice of an abstraction yet as the compilation file. The only thing that the compilation file needed was to change where to look for. And this is kind of important because if I don't do that, I could change the code itself, like the new app.h, to have a pound include that gives an absolute path to where the header lives, but that is highly not portable. You want to just be able to say pound include helper.h. So that's what this establishes. And now, another thing that we'll do, since this is a module that has already been compiled, in this Makefile, we are going to assume that that is done. That is not going to change. We've installed this helper module into these directories, and it's no longer the responsibility of this Makefile to keep track of that. So when we are compiling, we do not really state that this depends on that header file anymore, because it's either properly installed or the whole thing will fail. But if it fails, it's not in this project that we have to fix it anyway. The error lies elsewhere. So the only thing that you really put in the Makefiles are the dependencies of your own project. The other dependencies, like certain libraries being installed properly, is sort of outside of the scope of the Makefile. And so likewise here, we're not saying that things depend on helper.o. So this can only be done once this module is really properly developed out, like it's done. And we've installed it. We're not still developing it. If you're still developing it, we want to recompile with a new version, the way to go about is to add one of those clean rules that we've seen that basically deletes the .o files, and then run make again, and now it will pick up the new version of helper. Okay, so that's what we just did, is basically a poor man's library building. Real libraries are a little bit different, but they're similar in structure. They have to be installed, so move to a certain directory. You have to be able to include the header files, so you need the -i, and there's some object code that has to be linked in. Now, for Unix libraries, the object codes are not called .o if they're libraries. They end in either .a and .so. The difference is in how the linking happens behind the scenes, but it's not so important for our current discussion. They also tend to start with lib, so you can kind of see that something is a library file because it starts with lib and it ends with .a or .so. Other OSs have different conventions on how they call libraries. So Mac does it differently and Windows does it differently. But what's nice is that once it's properly installed, that actually doesn't matter. The way you call the compiler and the linker, as we will see, is not going to depend on these particular conventions at all. So for a real library, a real helper library, no, so .a and .so do mean different things, but it's just a different way of implementing the same functions linking behavior. So let's look at the .a first, because that's the closest to an object file. So suppose helper was a true module and was installed properly in the HLP directory. We still have to say -i HLP include, because I think I've installed this in this non-standard directory HLP that the compiler nor the operating system knows anything about. So now it knows. And then instead of linking the .o, I'm linking the .a. It seems kind of silly, but this is just the first step. What we now want to avoid is that we have to specifically say where these libraries live, so something similar to what we did with CXX flags, but for the linking, so for gathering all the object files together. And we'd also like to get rid of the fact that we have to know this explicit naming convention of having a lib and a .a, and so that is a standard way. There's a standard way to do that. The first thing, to find the object files or the library files directory, is to add a -L to the linking command. So show that. So here's a -L, and there again you say the directory that the library files live in. So -L HLP/lib, and we put this in LD flags Your example codes of the assignments had all empty LD flags. Now they're going to actually have to work a little bit and have something in them. And that LD flags is just added to the link command. The second thing we have to add is something that's equivalent to this help/lib/lib helper.a. But the way that works is that whole thing gets abbreviated by dash lowercase l, and that is a horrible decision to do that because it looks just like a 1, but it's lowercase l and then the name of the library file, of the library. So not a file, but the library. So the library is called helper, and that's why it's dash l helper. And then the compiler knows what kind of platform it is on, and it will know to look for libhelper.a, just because we said .l helper on a Linux machine. And so even on a Mac or on a Windows machine, you would say dash l helper, and in Windows it would look for helper.dll, and for Mac it does something else. But we don't have to worry about it. So this way the make files become portable between different systems. Make sense? Okay. So what we're not going to do in this lecture is to see how we would create a library. So that step from the .o to the .a that we sort of took for granted here, we're not going to go into that. You could look it up if you really want to, but we're not going to ask you to create your own libraries here. We're going to, and that's not the only step you really want to do. If you want to do that, you also want to know how to distribute them and pack them up properly and all of that. That goes beyond what we want to cover here. We just want to know how to use them. And so this is what we have to do. We have to do a -i to find the include files for compiling, the -L to have the directories where the libraries live, so the object code for them. And then we have to specify which ones we want. If we just specify, say, ld-lib, so just -l helper, the compiler can say, I can't find this helper library you want. If I just do the ld flags and not ld-libs, then it's not even looking for the helper flag. Then it just added that directory to a search path, but it never gets to search for anything. So you need both in this general case. Now, because the directory has been sort of replicated, the name of it occurs several times in this makefile, it's actually better to just to avoid mistakes, to put those in variables. So in makefile variables here, I've defined a helper root. That's help. This question equals syntax means that it could be that helper root is already defined before I call make, and in this case, use that helper root. But if it hasn't been defined, set it to help. And then the other things are defined relative to that. So helper inc is where the header files are supposed to live. Helper lib is where the library files live. And then I just use those in the various bits and pieces. I've added a clean room rule here. So clean rules are particularly important when you're either upgrading this helper library, because the makefile can't know it. It's not part of its project. So make clean and then make will do that. Or when you're copying your files and by accident you added your object files to that copying to a different machine that doesn't like that format of object files. So make clean then also gets you at a proper standing point. A few notes on this general scheme. The C++ standard libraries don't need -L. So if you're using vector or CMath or any of the other ones, they don't need lowercase l nor uppercase L. There are standard directories for libraries. And if your libraries live there, you do not have to do -I or -L. So in Linux, those are user include, user local include, etc. And that pertains particularly to libraries that you might install through a package manager. So if you have a package manager, this is your own system, you're installing it system-wide, they will be put in those standard directories, and you only will need the -lowercase l. So just specify the name of the library that needs to be linked in, so that will provide the implementation of the functions that you're using. But in those cases will not have to specify -I or -L. You will also not need -I or -L for libraries that you use with the module load command on the Teach for the Niagara cluster. This depends on how the clusters have been set up and how the modules have been set up. But for Teach or for Niagara, if you're using a bigger cluster, you do not have to do that. There's a trick to make that work. I'll actually mention the trick in a second. And if you compile your own libraries in non-standard locations like the HLP here, you do need this. So for your own libraries in your own home directory, which you can install, you will need these -I and -L options. So there is no magic way in which it happens. Suppose you're on a machine, there's a library you need, but it either isn't in the package manager or it's on the Teach cluster where you're not allowed to install it system-wide. You might want to install it yourself, and you might have to install it from source. And so you can do that, but you'd have to. But unfortunately, the way that the instructions that you will find from most libraries are, they will tell you the wrong thing to do. So what if you want to install libraries from source in your own home directory? So not system-wide, and so not using sudo, for instance, that never works on clusters. So what you want to do is you want to compile this library with a given base or root or prefix directory. And so a very common way to install this on Linux, but you should always read the documentation. It will tell you how to install a given piece of software. But it's very common to have to do this set of commands: configure, make, and make install. Now, what configure does is it looks at your computer, at your software environment, and figures out a whole bunch of things that are particular about it, and creates a makefile for you. And so it's a fairly old technology, although it's still sort of maintained, the auto tools. But what it does is it basically creates a makefile that works on your system. That's its function. Now, one of the things that you can do is you can give it options. And one of the options that's almost always present is a -- prefix equals and then some directory. I've called it root here, but you would choose it. So in the past example, it would probably be HLP, right? So that's the directory, and it will then configure the whole thing to install itself into that prefix directory. Make will create the object files, and make install will do the copying over to this root directory. So there's a configure step, a building step, so a compilation step, and then an installation step into the directory you want. If you leave out the prefix, it will try to install itself into the system directories, but we're assuming here that you don't have access to that, so you'll get an error. Another often and common way is for libraries to use what's called CMake. CMake is really, if you think about it, as sort of a replacement of configure. It can sometimes be better in terms of portability to different OSs. That's all I'll say about it. But yes, if your library comes with that, it'll say something like you should make a build directory and cd into it, and then you should type cmake ... and then if you want to do it in a different directory, the equivalence to this prefix is -d cmake install prefix equals root. This is not often in the documentation of your library, so it's good to know that this is how you put something in a different directory. Now CMake, at least by default and on Linux systems, makes a makefile just as configure does. So the next two steps are just making and make install. And I think we've mentioned already that -j option to make, but it allows you to make different parts in parallel if the dependencies allow it. So this is going to use 4 of my cores at the same time, whenever the dependency graph allows simultaneous compilations like that. Now you choose the root, so it could be in your $home, but that means you now have a non-standard directory, so you'll need the -I and the -L. And then a final note, if the documentation says to use sudo or sudo apt install or something like that, it's wrong for anything except for your own machines. So it's wrong for clusters, and it could be wrong for your computer too, because you might not want to install it system-wide. You might want to play around with it, have different versions available. be able to blow them away when you don't like them, and in other words, control where these libraries live. We've done all of this. To use a library, we have to include a header file, just as if it was in the current directory. That's what the dash capital I flag is for, to make that work. We have to link with the library name. If it's a non-standard directory, we have to dash I and dash capital L. Alternatively, and this can be useful if you just have your own installation and you never change where they live, you can change some variables, cpath, library path, and LD library path in under Linux to basically make G++ look into more directories than the standard. So G++ has some standard directories. This is not one of them, but you can add your root include into the cpath, and then there is an automatic -I if you want. You can add it to the LD library path and the library path, and that automatically adds it to -L. In fact, you might have to do LD library path even if you did -L for libraries that ended with .so. So this is a fair thing to have to do anyway. As I said, all of these are done automatically for the module systems, but this is just a technique to make this work on your own directory. And whatever you do, always read the documentation. It might tell you something different because it has its own build system. I mean, these things happen. That's okay, but find out how to install it somewhere in your home directory. That is the essence here. Okay, so let's look at an example. That is all sort of abstract. And we're going to look at an example using the GNU Scientific Library. This is a fairly large library. It's a C library. It's not a C++ library. It's been around for a long time. It has many useful scientific routines. It can do things like finding where a function equals 0, so root finding, minimization, sorting, integration, differentiation, interpolation, approximation, statistics, histograms, fitting, Monte Carlo integration, simulating and healing, ordinary differential equations. It can deal with polynomials, permutations. It has a bunch of special functions. It can allocate vectors and matrices. So a little bit of the stuff that the RRA does also, but only for vectors and matrices because they are needed in the rest of the functions. But it's a C library, so that means that we have to deal with pointers and casts and the like, because C doesn't have references, and yeah, that has some implications. So let's look at an example. I'm going to flash this at you just to show the C-ness of this. This is a C++ code. It includes GSL roots. So the way GSL sets itself up when you install it is there is a root. In that root directory, there is an include, and in this include is another directory, GSL. So this allows for a hierarchy. That's why we do have to have GSL/GSL roots.h. Roots is a sublibrary, if you want, that that you can use to find the roots of a function. So here's a function, a cosine sine v plus wx plus bx minus cx squared, of which you want to know at which point is this function 0. So for which value is x, this is 0. Those are called the roots of a function. So we want to do root finding. And the rest of the code doesn't implement the root finding. It implements an interface to the GSL to find this. So we'll look into more detail at the end of the lecture why it is structured the way it's structured and why there's still so much code even though we're using a library. But you can already see pointers floating around. Here's a void star. There's some extra casts here. There's this arrow. There are funny pointers here too. So as I said, we're going to look at that a little bit more once we know, because this is one of the issues. Once we know what we really want out of this root finding. But for now, this is our code. Suppose the code works, is proper. How do we use it? So there's a lot of GSL stuff that all comes from the GSL library. And the rest is just wrappers. It's just setting up the computation. How do we compile this? So on the Teach cluster, we already have the GSL library installed, so we just have to load the GCC module to get G++ and the GSL library to get GSL. And now we've set it up such that you don't need capital I and capital L options, but suppose you did need those, then you can find the include directories for the GSL from a special variable that is set by the GSL module. So GSL module sets a variable called signet underscore GSL underscore root. That's where GSL is installed. So obviously root because it's root directory, GSL because it's GSL library, and signet just because if you wanted to install your own and you want to call it GSL underscore root, we don't want name clashes. So that's what the prefix is. The lib directory is in there too and defined, and so I can now use those two variables in the -I and the -L options, and things will work. I can compile my code, I can link my code with the GSL library, and it just so happens that that this code also needs a secondary library that's part of GSL. It's called GSL CBLAS. At some point, we'll get to what that is exactly. But there's two libraries that have to be linked to, and these are both specified here. So again, this is an underscore L, and for most options, you can put a space after the -L, and it'll still work. Yeah. Okay, so once I've compiled it, I can run it, and apparently I have some iterations. I have lower, upper, root, error of this function. The Makefile version of that is also not terribly difficult. We again will use the GSL root that is here. This should say GSL lib, sorry. So we can redefine or reconstruct these directories. And then we put them in the -I and -L. We have the LDI libs, and this is kind of how it works. Okay, so you see now why that a lot of this stuff on the bottom hardly changes. All of the specifics are in the variables, right? The CXX flags are everything that has to be passed here. So this is always going to look like this. The LD library flags with the capital L's or the LD libs, they live here. I don't have to mess with these commands. And this is especially useful when we have code that has quite a few compilations. These two could have done with just inserting these things in place and a clean room rule. But yeah, if I ever change where the GSL is and I don't have a signet GSL root because I'm not on signet, then I just have to change these two first variables and things can be made to work. The question mark equal sign here is can again be very useful. If you compile this on the Teach cluster, you can just type make. If you compile this on your own computer, instead of just typing make, if you have your GSL elsewhere installed, you could just define GSL inc and GSL lib separately and point to the right GSL include and lib directory, and then type make. And make will see that this is already defined and not assign it to that. That's exactly what the question mark equals means. So the whole point here is not to reinvent the wheel. So for root finding, there are actually very many ways to do root finding. You could implement them. You could not, but you shouldn't have to. They're all pretty standard. And in fact, root finding is a century-old technique, if not older. People did them even before there were computers. And so somebody must have taken these algorithms and put them in some code, and that's correct. And so one of those libraries that has done that is the GNU Scientific Library. It has root finding algorithms. So again, you don't want to implement this if there's a library that does it. And so now the caveat here is that although they are implemented and they exist, you can't really use them unless you know what they do or what they need as an input. And so if you know a little bit of how they work, even if you don't have to implement it, it will help you understand why you're calling those functions with the parameters that you're giving and how to sort of properly use them. So let's look at root finding for a second. Look at a few of those classic algorithms to find roots of functions. And then we'll go back to that GSL code and see why it now sort of makes more sense that we have to do what we're doing. So root finding is a very common problem. We want to solve an equation numerically. Here's the equation. There's some function of a variable x that is 0. And when when this is true, then x is called the root of this function. We can make this multidimensional by having several functions f of several variables x that are all 0 at the same time. So that's a multidimensional root finding. That's a much harder problem. There are not that many algorithms that can do that reliable. The 1D case is a lot simpler to do, so we'll look at that first. So here's an example. Here's a function f. This is actually the function f that is in the code that we showed in the GSL example. So the purple line here. Now, I think most of you might realize this, but if you're not thinking numerically yet, so then you might say, well, why am I doing a numerical analysis to find a root? It's right here. But of course, we've created this graph by computing f of x for a whole bunch of variables, values, and we would have an idea of kind of where the root is already roughly. And so we'll just plot them and go, okay, hey, there it is. Imagine that computing f was kind of expensive to do. Generating this whole graph would have a lot of points that are completely pointless, pun not intended, because the 0 is just there, right? So imagine that you do not have the time, computational time to do a sort of full scan of all the function of x. You need a better way to find a root with as few evaluations of f as possible. So whenever I have a value of x, I have to find a value of f. I want to do that as few as possible. And so that's the game. And you can kind of tell that this is an old game because, yes, I know in the 1800s, you would have to compute this function by hand. And so you don't want to create this graph at all if you can help it. So this is a 1D function, right? It's a function of one variable. What's nice about 1D is that if we know that f is continuous, and say we do know that, then you can find if there is a root somewhere in an interval by considering, let's say, an interval a, b, by considering f of a and f of b. If they have opposite sign, then you know that the function has to pass through 0 somewhere, right? And so when that happens, when we have 2 points x called a and b, such that their function values have opposite value, we say that we have bracketed a root. So there's a root, we have an a and a b, and in between there, it has to be there, right? And so that's really the principle of a lot of these algorithms, where what we will do is we will try to find such a bracketed bracketing interval. That's a bit of a guesswork, but once we have that, we can do consecutive refinements to get the interval to be smaller and smaller and sort of zoom into a root. Right? Now we have to find this interval first. So you could do this by plotting the function, but with like not that many functions. Or you could say, make some conservative guess and say, look, this is a function, all the values in this function are of order 1. So let's try from -10 to 10, and that's probably good enough. Or do a wilder guess and say -1,000,000 to +1,000,000 and see if there's a sign change, right? You could make a smaller guess and expand if it's not like this is not as predictable an algorithm because you don't know what the function is, right? But so this depends a little bit on how much you know of the function. You might actually know roughly where it lives. You might have an approximation. These things can happen. And so even if you try to do this sort of automatic, there are cases that give you trouble when you try to find the bracketing. Here's a minimum that is also a root. So this is supposed to be the 0 line. So it is 0 here, but because it's a minimum, there is actually no sign change, and there is really no good algorithms that can find this. In fact, just by numerical round off, this might just be 0 or just below a 0 or just above a 0. It might actually numerically be sort of undefined whether you could find this 0. This here is another troublemaker where there are two zeros, but it's very close to it. So if I try A here and B here, I don't see a sign change and I go, there's no root. So it's not guaranteed that there is no root, but even refining it might make it hard to find this. Or it might not be a continuous function after all, like the singularity here, where there's a sign change, but there is no root either. So you can bracket a function only really properly when you kind of know something about it. Yeah, that part is not standard, say. But suppose we have found a bracket for our root. What's next? Well, we can do a couple of things to improve this bracketing. And since this is a numerical method, our answer is never going to be 100% correct because we only have, what is it, like 17, 18 significant digits in our double precision floating point. So we can't be more precise than that. If we needed more digits, we will never get them. So rather than aiming for like perfection, which we cannot attain, we will just say what's good enough. So we want the brackets to become smaller and smaller and smaller until it's a certain size that we are okay with. We say we are fine with knowing there's a root within this this tolerance, in other words, in this size of an interval. So the most classic of root finding algorithms is the bisection. There's others, and we'll very briefly look at them, but we might not have time for that. By the way, these sort of classic root finding algorithms are all for generic root finding problems. If you have a specific case like polynomials, so you want to find the roots of a polynomial function, there are special routines for that. If you have an eigenvalue problem, which so you have a matrix, you want to know its eigenvalues, those are the solution of a polynomial equation. So that's a root finding problem, we would say, but that is really not the way you want to solve this. There's a lot of structure to eigenvalue problems, which means that there are better methods to do this. And so we're going to go into linear algebra routines for that, but we'll look at linear algebra later in this course. So if you know more, if there's structure to your problem, you might not want to use these. But if you just have I don't know, this is just some function I need the root of, then you can use these. So let's look at bisection briefly. So here's our function again. We take our first guess for A and B. So I've called them A1 and B1, and indeed the sign has changed. Note I haven't even put the numbers on it anymore, but you could see what they really are. And then in bisection, you're bisecting this interval. You take the midpoint of the interval and you figure out what the function is at that point. And once you know that, you can see if it has a sign that is positive or negative. And so you're going to take either the first half of this interval or the second half, depending on which one has a sign change. So one of them has to have a sign change. They can't both have the sign change, right? So you'll take the one that also has a sign change. And this is by definition half as small as the previous interval. So if we keep repeating this, we will successively decrease the size of this interval. And we can do that either until machine precision, which might take a while, or until we have hit this tolerance level that we set. We'll find another midpoint, try again, another midpoint, etc. So we can go on forever if you had infinitely precise numbers. You could go on until a tolerance level, and that's what you would do. So you'd see when A3 and B3 or A and B are close enough together, you say, that's it, stop, give me the results. Okay, upper bound, lower bound, maybe even the guess for where it is. Now this is the bisection method, so that's pretty simple. Here's another one, false precision. Because one thing you could do is say, okay, I know the function values in the previous method. I was only using their signs, so I'm computing these values. I'm doing nothing with it. So there's some information I'm throwing away. Can't I use that? And the answer is yes, you can. So you start with the same roots, but rather than saying, okay, let me take the midpoint, you're going to make a linear approximation of the line between here. Now, that might be a bad approximation, might be a good approximation, but if the interval is sufficiently small and the function is sufficiently smooth, and of course, that depends, then this is an approximation, and it gets better and better as the interval gets smaller. And I solve the linear approximations route, which I can do exactly, well, numerically exactly. Anyway, I can have a formula for that I can evaluate. So it gives me this point here, right? And now I evaluate. It's not going to be perfect. It's not going to be the 0, because that will only be the case if it is actually a linear function, in which case I can probably see that. But what you compute is fx, and now you inspect its sign, and you do the same trick. If there's an opposite sign on the left interval, that's the one you're using. If there's an opposite sign on the right interval, you use that interval for the next interval. So you get your new bracket, and you repeat, you make a linear approximation, you check where the 0 of the linear approximation is, there we go, and you check its sign, and now we find that this is the sign. So because we're using more information that we already had, so we don't need more function evaluations. In fact, we use more information. It turns out that helps us get to the answer quicker, or get to our tolerance level quicker. There's other ways that just use function values. There's also a way to use the derivatives if your function can give you that. So these are non-derivative methods, secant methods, Wheeler's method, Brent's method. Brent is pretty nice in terms of speed and stability, but they all use different fits if you think about it. So just not just a linear fit, you could have, say, an exponential fit, for instance, which Ritter method does. Depends a bit on your function, which is best, but the more information you use that you have, if the interval is small enough, the faster you'll get to your answer. Here's a method that doesn't use bracketing, but uses derivatives. Okay, there's a question whether there's a C++ library. I think if I'm reading that right, for doing this. Yes, I'm pretty sure there's something in Boost that can do this. The point being here really is that since you're already using a library, it shouldn't matter that much what function, what language it's written in. It could be a Fortran library for all I care, if it does the job. But I do have to worry about the interface. So like there can be some advantage in staying with C++ just because of the simplicity of the interface. But if it's a well implemented method of something that really is central to you, you'll just bite that bullet, and you'll write that once, and it works. Okay, so just going back to Newton-Raphson for a second. This is a method that also finds roots, that uses the derivative. So suppose I know a function, but I also know its derivative, then here's a method that can also work. So I started a single point, some sort of guess I made. I check the derivative at that point, and then I make a linear approximation using that derivative to see where the 0 would be if it was a linear function. And then I do the same on that same level. So I compute the function and its derivative, and I see where the root would be. And that has a really fast convergence. Like it converges sort of quadratically faster than the bisection. And part of it is because we're using extra information, right? So the idea here is that the derivative would be easy to compute along with the function, for instance. Variants of these methods are used to do like artificial neural networks and the like, not entirely finding a root, but doing something similar. This is, however, a possibly dangerous method. So it's nice because it's really fast in how it converges, like much faster than the other methods, which means less functional evaluations. But you could imagine, say we started guessing x around here, then our method would have thrown us very far away from where we really want to be. And it really depends on what the function is doing further and further away, whether we will ever make it back. We might, if it's sort of a bounded function, or we might never find the root. So it can be unstable. And so that is unfortunate. However, if your function is smooth enough and the derivative is also smooth enough, then this is very fast. But you don't know that beforehand. So I put a little graph here on what the different convergence and stabilities areas are, properties are. So convergence measures how much smaller your bracket is, basically, or your accuracy is compared to the last step. Bisection cuts the error in half every time. The others have different ways of doing this. Some are just absolutely stable. Some might not guarantee to find the solution always, and some are just possibly unstable. And then there's ways to combine this. You can have methods where you might do bisection for a little while until you sort of are close to the root, and then you very quickly go into the solution by doing Newton-Raphson, because now it's smooth enough on that scale. Okay, so that is about root finding, and the real reason I'm mentioning it here is not because I want you to implement these. The actually opposite. Oh, there's multidimensional root finding, and I almost forgot. This is harder, and that's all I'll say about it here. This is harder because I can't bracket a root with a finite number of points in multidimensional space, right? In one-dimensional space, I have a line, and I can take two roots, and then that delineates everything in between. In a 2D space, I can have some points, but I've never bracketed the root, right? So there could be weird things going on. So this is trickier. And so often what people use is Newton-Raphson for these cases, combined with some sort of clever way to get close to the root. And even that is not as straightforward as 1D, because the derivative here is a matrix. So the function is a vector. The x looking is a vector. So the derivative has two vectors, means it becomes a matrix, and we have to find the inverse of this matrix, or we have to solve a linear equation. So we'll get to linear equations and linear algebra routines later, but that's what you're going to have to be using here. And this is even more close to what happens in neural networks and how they find ways to approximate or model input and output. Okay. Convergence stability, I kind of said this already, but because it's Newton-Raphson, it can be unstable. So there's ways to sort of to make that a little bit better. These are also in the GSL. Like the GSL is pretty big in terms of the things that it offers. Another reason why picking other libraries might be not always great. If you need a lot of different pieces, having just one library can be kind of nice. So let's end looking at this GSL roots finding example again. And let's just go through it and see all of these bits and pieces of essentially boilerplate or interface that we have to take care of. Because it's set up in a very, very general way. So that's one thing. And it's a C library. So let's look. We have our include of the GSL roots library, or the header file. And then this function has parameters A, B, C, and V and W for some reason. I want to be able to pass those to a function, right? But the GSL is a general library, so I have to be able to handle functions that take any number of parameters. And those parameters don't even have to be double precision. They could be some other variable. And so since the GSL library cannot assume how many arguments, how many parameters I will have, I have to wrap them all together into one thing, and that thing will be a struct. So there's a struct of parameters, and all it does is collect together these 5 parameters. Okay. Now, it has to be a struct, not a class, because C doesn't know classes. So it's just a plain struct that combines these 5 values. I have to pass the function to be of which I want to find the root. So I have to write the function in C, C++, C doesn't matter in this case. And so that function takes X, but it also has to take the parameters as an argument. Basically because there's no other, there's a way, it has to have a way to get access to the parameters, and it does it by a second function argument. But because it can't know how I've defined my structs, They might not always be struct params. Sometimes they might just be a double, for instance. So, so what I have to pass is a pointer to this structure that can be of any type. So that's a void star. A void star is pointer to anything without any more information. It's a way to escape the type safety of C++. You just make it a void star and it points somewhere in memory. As a memory address, it's still valid. For anything else, it's not particularly useful until you know what it is. So we will pass in a pointer to a struct params. We know that ahead of time, so that the way we will use this param parameter is first to cast it back to something that is of appropriate type. So the appropriate type here is a struct param star, so pointer to param. So I'm storing that here in the value p. So param and p point at the same thing, but the compiler now knows or trusts you that this points at a param, and then when that's the case, then p with a arrow, so this is an arrow a, gets the a out of the pointer of p. If this were a pure struct, then we have p dot a, but it's a pointer to a struct, so it's p arrow a. So there's a question if we couldn't just say param, and the reason we can't do that is that we have to give this function to a GSL routine. So the GSL routine will have an argument that expects a function, but functions have a type too. So if I made this into param, or params param, for instance, then this function would no longer be of the correct type that GSL can accept. So that's why it does this this void star business. The function type has to be general. They just decided on double precision as being specific, but it has to be general. And so the only way I can do that is to, excuse me, to pass it a void star. Okay, so that's my function. Then the int main defines my my lower limits initially, the upper limit. I define the parameters here. Then then I have to do two things. I have to decide what solver I want to use. So in GSL, there's this generic solver type called GSL root F solver. And so we're going to need one of those. In fact, we need a pointer to it because there's some dynamic memory allocation that GSL has to do. And we have to define the function in a generic way. And the way it's defined is there's yet another GSL specific type called a GSL function that wraps our real function. So it's a function wrapper if you want. We will first create the solver. As I said, there's some dynamic memory allocation that is necessary here. Because this is a C library, we can't do this with a constructor. So we have to, but there is a function that GSL gives to you. So there's a GSL root F solver alloc. And then I have to say what type I want. So I give the type of solver, it's Brent, and I allocate enough memory for Brent to do its work. After that, I construct the wrapper function. So the fwrapper function has two member fields, if you want. One that's just called function, which has to be exactly of this type. So that's what we assign it to. We assign it to this example function, which is of the correct type. This is the one that would have failed if this were if I put in just the actual parameters type here, because it would have said there's a mismatch of types. And then the same wrapper will also contain the arguments. So I'm going to pass the arguments in there too. This is a void star. That's why I take an ampersand of the arguments. The way it works, because void star can't point to anything, I didn't need a cast here, but it would have been a little bit clearer if it said void star ampersand args. But that's what this is. This is the void star to the parameters. Now that that's all set, I can start it off. So I'm going to start the solving, but the solving is something that happens iteratively, right? Even the bisection is iteratively. So we're initializing it now. I'm giving the solver, I'm giving the wrapper and the initial bracketing. And then I start my iteration. So the iteration goes here. Every iteration is done once. Once I've iterated, I can ask what is the current best estimate for a root? What is the current lower limit for my bracket, a high limit for a bracket? So there's functions for that. And then I'm just printing now to the screen. And there's a way to now test whether this interval is small enough. So I'm going to do a test of this interval, x low, x high. And I want it to be of a relative tolerance of 10 to the minus 3. So that's what this is. You can also do an absolute tolerance. I've chosen to not do that here. The status will be 0 when that is correct. So I'm going to keep iterating until the status is 0, which means that it is within 10 to the minus 13 of the answer. Okay, so we've got our tolerance, we've got our iteration, and we're printing out the intermediate steps, which you might not always want to do, but for now is a useful thing to do. So that's why when we printed things out, it had those lines. It has a lower limit, an upper limit, and an error. So it gives an error estimate by just doing the difference between the two. Okay. So yes, it's very elaborate, but what it is really doing, if you think about it, is mimicking an object-oriented programming paradigm, but in C. So this solver here is like an object, but because we don't have in C this idea of member functions, we can't do solver dot something, and that's why we have functions for everything that we pass solver to. Right, and so we have to live with that a little bit to be able to do this, but none of the implementation, we don't even have to know anything about the Brent algorithm, except we probably want to know whether it will give us the right result to use this. So the initial x low and x high, that's the question here. And I'm setting that here. So no, I have no way there is no general function that you can call to say where you should start. It's just something you kind of have to guess, or have to guess and then allow for some other self-written function to try and either limit it if it doesn't give a bracket, so make it smaller, it's not until it gives a bracket, which might fail, or make it larger. The thing is, whatever automated process you come up with in those cases can never be guaranteed to work. So those are not part of the GSL. That's something you either have to find by knowing something of your function. So you kind of go, all of these are like between 0 and 1. So let's take a nice, comfortable range. Or you might have just tried a few cases and you say, I can kind of see that the function keeps up going up on one side. So that's my end, and down on the other. That all depends completely on your function. Okay. Any other questions on either the root finding or the way we can use the GSL? And the GSL is not the only library that is C-based. We'll see some other ones, and so this interface is a very common thing that we will see. It's not. People aren't going to rewrite their libraries in C++ because they spent many years writing it in the first place, just because you like the interface to be nicer. Even if it would be nicer, it's just not worth their effort. Okay, all right. So we will see you. I pronounce GNU as GNU. That's a question. How should you pronounce GNU? I'm sure some people say GNU, and some people might not say anything. I don't know. I'm going with GNU. Yes, that's another way. If you're really, if you want to be precise, you can just say GNU. I actually don't know anybody that says that. But we will see you guys, or a bunch of you in any case, if you want, tomorrow for the office hours, and otherwise at the lecture on Thursday. So thanks for sticking around, and have a good day.